In Module 9, we're going to talk about how we integrate the ACI fabric into external Layer 3 networks through routing protocols such as OSPF or BGP, or even static routing. We'll talk about L3 configurations and design considerations, as well as design considerations overall for integrating your ACI fabric with your Layer 3 networks.
All right, let's talk about the need for connecting L3 to the outside world. For L3 integration outside of ACI, should be fairly evident. Data centers don't exist in a vacuum, of course, so they connect to outside networks through Layer 3 or Layer 2 means. We've talked about Layer 2 means in the past section. In this section, we're going to talk about Layer 3. So we've got, for example, here we've got Tenant Blue, and we've got 2 VRFs, 2 contacts, a couple of bridge domains apiece, and we're going to need to be able to have the subnets in these bridge domains communicate with the outside world. So we're going to mark them as public, and then we're going to exchange information with outside routers, either static routes or more likely some sort of routing protocol. So we can announce routes from the outside world into ACI and announce networks inside of ACI and have them distributed to the outside world. So that's just basic data center connectivity. In ACI, we do that on a per tenant basis. Typically, we'll go into, for example, tenant, and then here's tenant T06 under networking. We saw the external bridge networks before, and now we have external routed networks. So we've got an external routed network called BGP all the things. So here if you click on networks, you'll see we've got VRF, bridge domain, L2, and L3. So we have our L3 out, and this is called BGP all the things, connected to the VRF route table. And then under VRF route table, we have a bridge domain called cloud. So on our L3 or on external routed networks, we're going to need to have some sort of physical connectivity to the outside world, and we can do that. Our networks to the outside world are going to be represented by networks. So these are considered outside EPGs. So inside the EPGs we've been talking about beforehand have been encapsulations such as VLAN or VXLAN, and they represent inside of the ACI fabric. Outside EPGs are outside Layer 3 EPGs are Layer 3 networks that come from the outside world. They're defined by their subnets. Now, in this case right here, we have Internet as an external Layer 3 EPG, and that's represented by 0/0. So that's the entirety of the internet. We can do more specific matches. So these are LPMs, longest prefix matches. So we can do /8, /16s, even /24s, or in this case, we're just doing a catch-all for the entire internet. So L3 configuration. So we have in ACI, we basically have two control planes. We have a single data plane, of course, but we've got two control planes. So which forwarding space is used to forward the packet is determined by which IP network it is in and where it is going. So routes learned from peering routers, routes learned from the outside world through routing protocols or static routes are marked as outside. Frames that arrive from an endpoint that is inside of a tenant space, something inside of the ACI fabric from one of the bridge domains or internal subnets, that is considered an inside. That's an inside route. We use two different methods to distribute those routes throughout the fabric. So if the IP destination is outside the ACI fabric, forward to the TEP to the nearest external router. So we call this a border router or border leaf router. If the destination IP address is inside the tenant space, ACI forwards it to the TEP where the destination endpoint is. So in this example here, we've got a virtual machine, or it could be bare metal, doesn't really matter. It's sending a packet to the outside world. So that's an outside address, and then here it's sending another packet to an inside address to a local switch. Layer 3 distribution. In ACI, the routes that we learn from the outside world, those outside routes, we need to distribute them to the other leaves. So when we build a peering session, like for example OSPF, we're announcing routes to the router potentially, or most likely, and we're taking routes in from the router through some sort of routing protocol or static routes. And we need a way to take the routes that we've learned from the outside world, and we need to distribute them to the other leaves. And we do that through a BGP route reflector. We're using MP BGP for distributing external routes outside EPGs to the other leaf switches. So the border leaf switch can peer with external networks and then redistribute internally. Only public subnets are announced to the external network. So only networks that we have configured. The little checkbox when you configure a subnet, you have that option for either for a private non-routed or not routed, a private network that's not announced outside of the ACI fabric versus a subnet that's announced outside via routing protocol. To connect to the outside world, so we've got this session here, we've got a router here, we've got a connection to this leaf. This leaf's going to have an interface. We've got a couple of different ways that we can set up a peering session with that router for routing protocol purposes or even static routes. We can go with routed interface, so there's a standard layer 3 routed interface. So if we've got a 10 gig link, that becomes a layer 3 10 gig interface, similar to no switch port on a Nexus. We can do an SVI and then attach that VLAN or trunk that VLAN down through that physical interface. Over here we got VLAN 3069 for this SVI. We can also do routed subinterfaces. So it's like a routed interface, but instead of the entire interface is that IP address, then we're carving it up using 802.1q. We've got a couple different protocols we can use. We can do IBGP, OSPF, as well as EIGRP. So to configure this route reflector, you're going to need to have at least one route reflector, typically 2. Now you can do multi-pod configurations now, and that's covered in much more detail in the multi-pod, multi-fabric section. But you're going to need to have some sort of BGP route reflector configuration, and you put them on the spines. Typically at least 2. You can have up to 6. In most cases, you're going to have 2 because most installations tend to have 2 spines. In this diagram right here, we've only got 1 because it's a lab environment. We only have 1 spine. But you go into Fabric, you go into Fabric Policies, under Pod Policies. Now remember, you can do multiple pods. Every pod is going to have its own route reflectors. And even if you're not doing multi-pod, you're still got pod 1. So if you have an ACI Fabric, you have pod 1. And the only difference is whether or not you're going to have more than 1 pod. So we configure the route reflector for pod 1. We set the node ID, and then under policy groups, so that'll be policy groups here. It's kind of cut off from that image right there, but we see ACI pod, and then under here we have resolved BGP route reflector policy. So we can create multiple of these policies and bundle them together into multiple policy groups, and then have each one of those policy groups assigned to a different pod, so that way we have different BGP route reflectors and other SNMP policies. Maybe we're sending SNMP traps to different collectors in each pod, etc. And again, we cover multi-pod in more detail in a different section. So routing, OSPF routing, for example, we use VRF Lite for tenant route separation. So we've got multiple VRFs here. Let's take a look at the configuration in this router here. So we've got interface E11.1000. So this is a sub interface. We're encapsulating on .1q 1000. So that's VLAN 1000. VRF member tenant 2. IP address. So this is a /30. So this is a point-to-point. We give it a router ID and an area. So area 1. So under router OSPF 1, we've got VRF tenant 2, area 1, not so stubby area. And so we build that session there. So we're doing multiple VRFs, and then each of those VRFs will get distributed via the route reflector into the different leaves. And the VRFs, of course, even external routes that we learned through outside networks, these are separate VRFs, separate routing instances, or not separate routing instances, but separate routing tables. So we do delineate between them. So we can have overlapping external routes that we learn and overlapping internal routes that we announce to the outside world. So tenant public subnet is redistributed to routing peers on the border leaf. So we're going back and forth. Only the leaves that have tenants instantiated on will actually get those routes from the outside world. So the route reflector will distribute them to all leaves, but only the leaves that have those tenants will actually install those routes into the hardware cam, into the TCAM, into the forwarding tables. So we're using MP BGP peering between leaf and spines through route reflectors. So for an example of how it goes back and forth, we take a look here. We've got a couple of virtual machines. We've got a couple different subnets. So this is tenant green. We've got a subnet, a public subnet 100.1.1.10. I'm sorry, 100.1.1.1.0/24. So this means we're going to advertise this to the outside world. We've got 10.1.1.0/24. That's going to be a private subnet, so that's not going to leave the fabric. So that's something typically like east-west traffic. We had a VM on each one. So 100.1.1.10 is attached to this leaf. So this leaf redistributes the route through the route reflector to the border leaf and then announces it out, summarizes it out through to the router. So the router sees the 100.1.1.0/24 on that interface. We are taking 200.1.1.0/24, so that's the public, that's not public, but that's an external route. We're announcing it into the ACI fabric through that peering and then into the route reflector, and then that gets instantiated into the forwarding tables of that particular leaf. We can do IBGP, so we have a router here and we've got IBGP going on. The ACI fabric will require its own AS number, so one AS per fabric. And then we can do IBGP peer to a router, and then we can do EBGP to the outside world. So why would we want to do that? Why can't we just do an EBGP peer to the leaves? Well, the leaves are data center switches, and data center switches typically are built with different allocations for their forwarding table space. The internet routing table is something like 600 to 700,000 routes, so we need to be able to install 600 to 700,000 LPMs. And the 9300s don't have that capacity. So that's not something we typically scale out to multiple devices. Remember, TCAM space is at a premium and it costs a lot of money. And power, the more entries you have in a TCAM. So that's why we typically have different hardware. So hardware is designed to be a customer edge router. It's designed with less interfaces but more TCAM. And then, of course, data center switches, even if they're layer 3, are designed with a smaller TCAM space because we're scaling that out. We're scaling it horizontally. So if we have a large routing table or a greater number of VRFs that we can't do in the leaves, or WAN features and more sophisticated BGP policy, the ACI fabric is a data center fabric. So the technology and the software is built to be inside of a data center. So use the right tool for the right job. So typically there's edge routers from Cisco and other vendors as well. So internal to external EPGs. For the L3 outside connection, an external EPG is derived from the subnet. So we differentiate via subnets. Over here on the right, we've got two external EPGs. We've got external EPG 1 and external EPG 2. External EPG 1 is 100.1.1.0/24 and then 100.1.1.2.0/24. EPG 2 is 200.1.1.0 and 200.1.1.2, both /24s. So that's how in an internal network, an internal EPG rather, is typically some sort of encapsulation, such as VLAN or VXLAN. And external EPGs are LPMs, longest prefix matches. So they could even be /32s for the outside world. Typically there'll be something larger. They can even be 0/0, as you saw in the earlier example. And we've mentioned the local station table and the global station table on each leaf. We also now introducing a third table, the LPM table. So this is the longest prefix match. The global station table and the local station table they're both /32s or they're MAC entries. So they're specific entries. Or we have the default route in case we don't know where to send anything to. We'll send it to a proxy. And then we have the external LPM table, and that's more of a longest prefix match, whatever route we have that has the more specific. So if we have two entries that overlap, the one that is more specific is the one that wins when we talk about LPM. So the external LPM lookup table with the destination IP. Again, everything in ACI is hardware forwarded, so we're not putting anything into a software router. So all this stuff is done in the TCAMs. So we derive the destination EPG by checking the destination EPG by checking the destination IP. So we have 10.1.1.3.11. Let's say it wants to send a packet to 10.1.1.1. So that's /24. Leaves the virtual machine, goes into the leaf. The leaf will check its table. Okay, 201.1.1 is not in our local station table. It's not in our global station table. And rather than forward it to the proxy, we're going to check our external LPM table. Okay, now it matches 201.1.1 is certainly included in 2110/24. So we're going to forward that packet to leaf 6. Okay, packet goes to the tap address of leaf 6. Leaf 6 will then check its external LPM table. 201.1.0/24, it matches that. It's going to go to external EPG 2. Now, the whole reason why we're doing these external EPGs and classifying them via their LPMs, the longest prefix matches, is because we need contracts. We need a contract in order for this external EPG to communicate with the web EPG that this virtual machine is inside. Same thing for external EPG 2. By grouping them into EPGs, we can both provide and consume contracts for external layer 3 networks. And then we apply a policy based on source, destination, EPG, and contract. From the external EPGs for the L3 outside connection. So from an L3 outside connection, the external EPG is again derived from subnet. So when we create an external EPG, an L3 out, we have to define it as a subnet. Again, it could be a /24, or it could be just 0/0 representing the entire internet. We can have multiple external EPGs. For example, one external EPG could be the internet, another one could be sales office, another one could be your development office, etc. So we have to have different contracts for different EPGs. So the EPG 1 can have one contract, EPG 2 can have more than one contract, or can have different contracts. They can have contracts common, they can have different contracts. The same provide and consume model that we do for internal EPGs. When a packet comes in, we check the source IP address against external EPG mapping and derive the source EPG. We mark the source EPG in the VXLAN header. Step number 2, we check destination IP address in the global station table. We derive the destination IP and then send it to the egress leaf. If missed, we send it to the spine for the proxy. So if we don't, the proxies know all. We try to apply a policy at ingress in case there is a hit on the GST. If there is a miss, we can apply the policy on the egress leaf. So we can do the filtering, we can apply the contract rules on ingress or egress. ACI supports IGMP snooping for layer 2 bridging for IP multicast traffic. So typically ACI will not route multicast. So we use IGMP snooping. Normally we'll need an external PIM router for layer 3 routing across the bridge domain boundary. However, as of ACI 2.0, any of the EX hardware is capable of routing multicast now. So there is the ability to route multicast, but you have to use the EX hardware. So that's the 93180 EX and the 93106 or 108. So let's say traffic was leaving EPG 1 and was destined for these two VMs and two different EPGs. This is all in the same bridge domain. So you'll note that the traffic gets forwarded to the leaf, from the leaf to the spine. The spine will then forward it to the leaves. So the replication happens at the spine rather than happening at the leaves. If we're going to need to route multicast, we're going to need to send it to a PIM router, to an external PIM router. All right, now let's talk about L3 shared out. The default style used to be that you would set up L3 outs for every tenant. So every tenant would have its own interfaces or sub-interfaces doing its own peering with its own routers, multi-tenant. But that may not be an ideal scenario, especially if your tenants, here we have Coke and Pepsi, but what if your tenants are just two different projects in the same company? You're going to share some routing resources, so we don't need to split multi-tenancy off that much. So there's a way that we can share the L3 outs amongst multiple tenants, so we only have to have one or much fewer routing pure L3 outs and routing sessions with external routers than we do tenants. So in this case, we have two tenants, but we only have one L3 out. So there's a couple ways we can do this. One way is we put the bridge domain and subnet and L3 outs under the common tenant. So we have bridge domain Coke and bridge domain Pepsi. They all have their own individual IP space. and all of our endpoint groups in each of these tenants exist in their own individual bridge domains. So we have, for tenant Coke, we have web app and DB, and their IPs come from the bridge domain Coke. And they all share the L3 out, and they all share routing with an external routing protocol, either dynamic routing protocol or static route. We can't have overlapping IP addresses among tenants, of course. Now, normally in VRFs, we can have overlapping IP space, but since we're having the same IP space in the common tenant, they can't overlap. So that just makes sense. Bridge domains and subnet and L3 out are defined in the common tenant. EPGs, contracts, and application profile are under the individual tenants themselves. Another way to do it is to have your bridge domains inside of the tenants, but we're going to share the L3 out, and that L3 out is going to have that routing protocol. So this is, I think this is 1.3 and later. So the bridge domain, EPG contract, and application profile under individual tenants. The L3 out is the only one that's in a common tenant. So this might work out a little bit more smoothly for multi-tenant environments, even if it's just two different projects or two different groups in the same company. So prior to ACI 1.2, if you had two different VRFs, if you had two different tenants, then each tenant had to have its own L3 out, and then each L3 out had to have its own peering session with a router. They could be individual interfaces, or they could share the same interface, but they had to be sub-interfaces. So we would use VRF Lite. So maybe this L3 out used VLAN 10 to set up a OSPF peer with this router, and then this, if it was using the same port, this one used VLAN 11 to set up an OSPF, a point-to-point link, etc. But they could everything could overlap though. We just do different VRFs on the router itself, and we would route leak on the router. But now we have the ability to do L3 outs across the VRF instance now. So in this case here, again, we've got every VRF has its own bridge domain. We've got an L3 out. We've got an external EPG for shared services, perhaps, and then we can build contracts to multiple tenants here. So L3 out is under tenant common. All tenants have the same L3 out connection. Each tenant can access the shared services provided by the workloads and external EPGs, and L3 outs, we address the L3 out in external EPG scale. So this makes things more simple. We do route propagation through route leaking. So whatever routes we learn inside of the tenant common, so this will be its own separate VRF, we'll route leak into the VRFs of Coke and Pepsi. So here we've got 2020.20.0.24, so it's a /24, and it's being learned through routing protocols into the common VRF, and then it's being route leaked into the other VRFs. To configure a tenant subnet to leak, when we create under a bridge domain, we create a subnet and then advertise externally. That means we're going to allow it to advertise to the L3 outs. This just means basically that this particular this particular subnet 192.168.1.0/24, this /24 is going to be able to be advertised through our routing protocol. Shared between VRFs, that means we can route leak it between VRFs. Whether it's inside of the same, whether or not it's inside of the same tenant, or it's in, because you can have a single tenant can have multiple VRFs, so we can route leak between those, and then between multiple tenants as well. So this just allows route leaking. And then if we're going to configure external subnets, so here we've got tenant common, we've got networking, we've got our L3 out, we've got our networks, we've got one called PML. And it's 33.33.33/32, so it's a /32. And then we can configure it to route leak into our tenant VRFs. When we share external EPG classifiers across VRF instances, the forwarding table will mask out the VRF ID, so that way that these particular IP addresses are applicable to all VRFs. And normally policy is applied on the border leaf for leaving the fabric, with a shared L3 out policy for traffic destined for a shared service EPG is applied on the ingress on the leaf. And the same external EPG definition is used for all tenants and shared instances. So all tenants use the same copy of the classifiers to derive the class ID. So that's the class ID right there.